Hey folks, this lesson is on ionization energy, one of the periodic trends we are studying. So what is ionization energy? It's the amount of energy required to completely remove an electron from an atom in the gas state. It's expressed in kilojoules per mole. Joules, as you know, is a unit of energy, and mole is a unit of measurement, and we'll discuss that a little bit later. Now, keep in mind from our previous lessons, the greater the attraction between the nucleus and the electron, the harder it will be to remove it. This is going to be a key understanding in terms of studying ionization energy. So first ionization energy, there are a number of different ionization energies depending on which electron you're removing. And it's the energy required to remove 1 mole, again, mole being a unit of measurement, of electrons from each atom in 1 mole of gaseous atoms or gaseous atoms to form a mole of gaseous positive ions. So basically, again, it's using this mole as a unit of measurement as a standard. But the key idea here is that it's the amount of energy required to remove an electron from an atom in its gas form. The first ionization energy deals with the first electron. So if we have a atom, and here's our nucleus, we have this, in this case we're going to draw lithium. We have 1 electron here, 1 electron here, and 1 electron here. The first ionization energy is the energy to remove the first electron. Now the first one being the outermost. So that would be our first electron. Now we can also remove the inside electrons here, this one and this one. It doesn't really matter for our cases in which order it is. But if we remove the second of the 3 electrons, this would be our second ionization energy. And finally, if we move the last one, this would be our third ionization energy. So what affects the ionization energy? Well, it really does depend on the electronic structure. Now, if you look at it, if we look at our 3 values here, we have 1300 kilojoules, 2300 kilojoules for helium, and 519 kilojoules. So what you can see is that helium has the greatest value. And when we're looking at this, we have to understand why this is the case. Hydrogen is very similar to helium in that it has a proton and an electron. But helium has double that. It has 2 protons and 2 electrons. Now what that means is that helium will have a tighter or more attractive pull towards these electrons towards the nucleus. So there's going to be more of a pull towards that nucleus. Now remember what we just said. The stronger the attraction, the more energy it's going to require to actually remove that electron. So because helium has a higher nuclear charge, okay, it is going to have a stronger hold on the electrons. A stronger hold means that you'll need more energy to break that attraction. And ladies and gentlemen, this is our ionization energy. In this case, to remove this first electron, again, we're dealing with the first ionization energy, so the amount of energy to remove the first electron. Now, hydrogen only has 1 electron, so this would be the first ionization energy. Helium, we could choose either one of these. Let's just choose this one here. This would be our first. And lithium, again, lithium has 3 electrons. The first ionization energy would refer to this outer electron there. So in comparing the first ionization energies of all of these, helium has the highest one because it has the highest nuclear charge. It requires more energy, and therefore it is a higher ionization energy. Now, why does this one have such a low one? Well, think about it. This electron, again, is now not only in this outer shell, which is farther away, but it's also experiencing some shielding effect from these inner electrons. So because of the shielding and the distance, this one is going to require less energy to remove. Think about you holding hands with somebody. If you're holding on by wrists and you're really, really close, it's going to take a lot of energy to pull those people apart. But if you're holding just by your pinkies, it won't take a lot of energy to rip those apart. And this is kind of the same thing. So as we mentioned, kind of alluded to, there are more than one ionization energy. There's second ionization energy, third, fourth, fifth, etc., etc. And it really is just the measured amount of energy required subsequent electrons. So our first one is always the one on the outside. And in this case, if we look at our atom here, magnesium in this case, our first ionization energy would refer to this outer electron. Then as we kept removing subsequent electrons, this one would be our second ionization energy. And then we might have our third, our fourth, our fifth, our sixth, our seventh, eighth, ninth, 10th, 11th, and 12th ionization energies. So magnesium could potentially have 12 ionization energies. And as a key learning here, as you go farther and farther and farther into an atom and removing subsequent electrons, your ionization energy is only going to get higher. Remember that as you get rid of all these electrons, these ones here and here and here and here, okay, the amount of protons doesn't change. You're still going to have 12 protons, which means you're going to have a charge 12 plus on the nucleus. But if you only have now 2 electrons, 2 minuses, you have an overall charge or an overall pull of 10 protons kind of in excess. So you have 12 protons only pulling in 2 electrons. You're going to have a really, really massive pull, and that's going to require a lot of energy. So in the case of these examples here, when we have magnesium, if we want to get rid of 1 electron, our first ionization energy, for magnesium this would be plus 738 kilojoules per mole. So that's quite a bit, but let's see, if we got rid of this first electron here, the first electron right here, it only has 1 more electron to get to a full outer shell. It only has to lose that 1, and then it's going to have 8 electrons, and it's going to be pretty stable there. So we can expect the next ionization energy to be higher than the first, because again now we have more protons pulling in lesser amount of electrons. So what we do see is that this is going to be plus 1451 kilojoules per mole. So yeah, it is higher than the first one, but it's not that much greater. Let's see what happens to the next one. So right now, as we've lost two electrons, or 2 outer electrons, this one here and this one here, this Mg2 plus has a full octet, and it is stable. It wants to be there. Okay, magnesium always has a charge of plus 2 because it loses those 2 electrons to get a full outer shell. Now what we're going to do is we're going to force magnesium to lose 1 of its electrons. So what right now we're going to create is not an octet. Okay, it's going to be missing 1 from a full octet. So you know what? We're going to predict that it's going to be quite high. It doesn't want to lose that full outer shell, and it's going to put up a fight. So what we're going to see is that indeed the amount of energy is tremendously different. We went from 1400 to almost 8,000 kilojoules per mole. And as we go on, again, we're going to see a huge amount of energy. Not as big as a jump, because we've already lost that octet, but you still see a tremendous amount of energy that needs to be put in to remove that 4th electron in this case. So we've been kind of alluding to which electron does the first ionization relate to, the second one, etc. In this case, if we have this little graph demonstrating the different kilojoules per mole values with these respective electrons, and we're going to be dealing with nitrogen. So when we talk about the first ionization energy, we're talking about this outer electron, this one that's unpaired in this case. And then we'd go into our second, so our second could be any one of these 4 outer electrons here. We're just going to choose one and say this one. This could be our third, our fourth, and our fifth. Okay, so those would relate to these ones over here. And then we keep going. So what we can see is that there is a slight increase in the amount of energy that is required to actually remove these electrons. Okay, it goes up steadily from about 10,000, going up and up and up and up. But then we have this huge jump into these last 2 electrons. Now, those last 2 electrons are these ones in here, this one and here. Why the huge jump? Why going from 20,000 shooting up to almost 60,000 kilojoules per mole? Well, let's look at our electronic configuration to help us see that. Here we have our 5 electrons, our 5, in this case, outer electrons. Those relate to these 5 dots here. What do you notice when we get rid of all of these 5? We get rid of all this one, this one, this one, this one, and this one. we actually jump down into another level. This massive jump in amount of energy has to deal and usually represents a jump in level. Okay, so when you have a large change in the amount of energy required to remove electrons, it usually represents a change in energy levels. Alrighty. So in this case, we can see this in magnesium. We can see that we have this kind of, this graph represents the ionization energies of magnesium, and as you can see, we have 12 ionization energies because magnesium has 12 electrons. But if we look a little bit closer, we can see three distinct groups. The first one being pretty obvious here, okay, and these are 11 and 12, so it's more inside of the electron. If we look at the outermost electrons, we can see that these two kind of show an also kind of grouping. And then finally we have this grouping here. Well, let's see how this kind of works. Here we have two electrons here. Here we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 electrons here. And then finally, the last one, we have 2. So let's just write that here. I'm going to just put 2, 8, and 2. Okay, well, let's look at this. If we draw the Bohr-Rutherford diagram for magnesium, I'm just going to omit the protons here. We have first level, we have 2 electrons. Second level, we have 1, 2, 3, 4, 5, 6, 7, and 8 electrons. And our final outside has 1, 2. Well, look at that. It kind of proves what we were saying before, that this graphical data allows us to see where these, or allows us to kind of recognize the electrical configuration of our atoms. It does show a jump right here into a new level, and it obviously shows a jump right here into another level. As we get smaller and get closer into the nucleus, these energies are going to start increasing because, again, these electrons are closer to the nucleus. It's going to have a greater pull. A greater pull means it's going to be harder to remove, and harder to remove means it's going to require a lot more energy to do that. So this is the trend of the periodic table, and as you can see, there is a kind of trend or repeating pattern here. Here we have this massive spike, and it jumps down, and again we have this kind of moving on up spike, jumps down, moving on up spike, jumps down, moving on up, etc., etc. And if we pair this to the periodic table, what we can see is that these two first elements are the electrons that are found in hydrogen and helium. Okay? Then what we see is we see a jump down starting at lithium, which is right over here, going all the way across to neon. Alright, and then it jumps back down. It starts at sodium, goes to argon. So now we're talking about this one over here, and so on and so forth. So what we're seeing here is that as we go across the period, okay, so going from lithium, beryllium, to boron, to carbon, to nitrogen, oxygen, fluorine, neon, that's kind of represented here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, what we're seeing is that as we go across the period, we can see that there's going to be an increase in ionization energy. Okay? Remember, why does this happen? Think about your nuclear charge. Okay? Think about that nuclear charge. Now, the other trend that we see is that as we start going down the group, so here we have lithium, sodium, potassium, rubidium, cesium, you can start seeing that the amount of energies is getting less and less and less. So as you go down a group, you're going to have a decrease in ionization energy. So those explanations are over here. This is just an isolated graphical piece of data for the group 2 elements. So as you can see, we're starting with beryllium, we go down magnesium, calcium, strontium, and barium. So we're going down that group. And what you can see is that the ionization energies, the amount of kilojoules per mole, is actually decreasing. So think about it in terms of our factors. As we go down this group, what's actually happening? Well, we're increasing the amount of electrons. Those electrons require more space, so they need to go into new energy levels. As you start adding more and more shells, if we have a nucleus, as we start adding more and more and more shells with all these energy levels being populated with electrons. Here we have 2, we have 8, etc. Another 8, here 8. We have that one. This outer electron here, right there, has to see through all of those and is also getting repelled by all these inner electrons. So you're increasing the shielding from those inner electrons. If you're increasing the shielding and you're also increasing the distance away from that nucleus, you know what? The amount of attraction that electron will feel will be less and less and less. Less of an attraction means that it's going to be easier to remove, which requires less energy. And folks, we're talking about ionization energy, the amount of energy required to remove an electron. If it's easier to remove and it requires less energy, we're going to have lower ionization energy. When we're talking about our period and going across it, what we see is that starting from left to right, we are seeing this increase in ionization energy as we go from sodium to argon, and this is in period 3. So when we're looking at this, if we look at these different elements, and we start at sodium and into magnesium and aluminum, they have an inner shell that's full of electrons. We have another inner shell that has 8 electrons. And finally, an outer shell. And in sodium, it only has 1 electron. Magnesium has 2 electrons, and so forth. Aluminum would have 3. But what you're not changing is you're not changing the amount of inner electrons. That stays the same. All we're doing is we're adding more and more electrons to the outer shell. So that means that there's no change in shielding from these inner electrons. If the amount of inner electrons doesn't change, the amount of shielding will also stay constant. What you are doing is as you go across, you're adding more and more protons. Remember that sodium has 11 protons, magnesium has 12 protons, aluminum has 13, 14, 15, 16, 17, 18. So you're adding the amount of protons, which is increasing the positivity of the nucleus. Now you're getting a nucleus that is becoming more and more positive. Okay, and here you're going to have a really, really positive nucleus. And the shielding is not changing. So what that means is that there's going to be more of an attraction between this positive nucleus and the outer electrons. If there's a higher attraction, that means it's going to be harder to remove. It's harder to remove, which means it requires more energy. And again, as we're saying, we're talking about ionization energy, the amount of energy required to remove an electron. If it requires more energy, it's going to have a higher ionization energy. So here are some actual ionization energy values. What we're seeing before is that as we go across the period, so in terms of ionization energy, as we go across the period, and remember across means from left to right, what we're seeing is that we are seeing ionization energy increase. Okay, so we're talking about an increase in ionization energy. Now, again, as you went down the period, what you can see, not only from this chart, but from our discussion previously, you can see that ionization energy decreases because it has more shielding and is also farther away, so less of an attraction. So in our little table here, we can see that ionization energy increases as we go up a group and across a period. And that is represented here. So our first ionization energy, our ionization energy increases going up and across. So some real life uses of ionization energy can be found in mass spectrometry. It has applications in the environmental, pharmaceutical, and forensic world. And the way that this kind of works is that you have some kind of sample, it's bombarded, and it creates an ion. That ion kind of goes through this slit and is moved through this tube, this kind of curving tube. There's a magnet here, and when it actually kind of separates based on the molecular weight. Okay? And so here, and also if it has more of a charge or less of a charge, is also deflected differently as well. And it kind of moves on to this ion detector where it's detected, and we can create these different graphs. Alright guys, that's it for ionization energy. Stay tuned for our next periodic trend.